So in your packet, you need to have out pages 63 to 65. And this is going to be a continuation of regression by looking at residuals and how they affect what type of function we might feel is a best fit for a set of data. All right, so we've seen it is possible to use different shape curves or functions to model data. Choosing the curve to use, whether linear, quadratic, or exponential, was easy as long as the scatter plot showed a resemblance to the actual curve. When we were looking at regression on Friday, we also noticed that we could look at that r-squared value, and that would give us another mathematical value for us to look at to decide if it was a good fit for that set of data. But sometimes, as we saw, they would get where the r-squared values might be really close to 1 for a couple of different types of function. And if that's the case, then we need to have a kind of another mathematical way that we can possibly decide what might be the best set for that data or function for that data. So that's where residuals are going to come in. Right, so residuals help to determine if a curve shape or a linear versus nonlinear model is appropriate. The residual, the actual point itself, is the distance between the actual y value and then the y value you get when you do the regression equation and you predict the y value. So when you subtract the actual versus the predicted, you get what we call it, which is the residual. Right? If you get a residual of 0, then you're telling, or it is saying that the actual y value and the predicted y value are exactly the same. And then it says it is the vertical distance from the actual plotted point on the regression line, sometimes referred to as the observed error. So here you can actually see, right, a graph. And it's showing the residuals. The residuals are these little red lines that you see here, all these little red lines where it's measuring the distance between the actual regression equation, which would be the predicted y value, and then the one that would have come out of the table, the actual y value. So those little distances there are called the residual, the distance between where that point is and that regression equation line. Those little lines there are called the residuals. So that is a measure of distance between the y value and that line. When you look at a scatter plot and you're unsure if a curve shape should be chosen for your regression equation, right? If you create a residual plot, right, this could be helpful for you to figure out if it's the best model. So a residual plot, right, your vertical axis is your residuals, so that would be your y-axis, and then your horizontal axis is your x values. It says a linear model is appropriate when the plots are randomly placed above and below the x-axis. A nonlinear model is appropriate if the plot follows a pattern resembling a curve. So here it is giving you some examples of when linear is appropriate versus when a nonlinear is appropriate. So you can see in this first one here how these are all randomly spaced above and below. This is the x-axis, right? Above and below that x-axis makes it a linear is appropriate. These two here both have a U-shaped pattern to them, which indicates that a non-linear model is probably a better fit for that set of data. So randomly spaced above and below the x-axis for the residual plot means linear is appropriate. A U-shaped pattern, right, means that non-linear is appropriate. Right, so we got a couple of examples here where we're going to be able to look at some of these residual plots and then how we can calculate them. So I'm going to show you, this is going to be something that we're going to do in Desmos again, just like we've been doing all of our stuff with regression. So I'm going to start out by putting this data into Desmos. All right, so I'm going to start by creating myself a table. And I'm going to type those values in. All right, so we can see here it's a little hard to tell by just looking at this set of data, all right, what might be the best type of regression for this set, whether, linear, exponential, quadratic. It's kind of hard to tell by just looking at it. All right, let's next calculate that linear regression. And we can see here again, it's a little hard to tell. You can also see where, if you look at that r squared and that r value down there, again, it's a little hard to tell if we think that linear might be appropriate. It kind of looks like a line fits through them, but it's not necessarily the best, all right, but it kind of fits there. And so if we look here at our first question, it asks us to create it, which we did, and it says look at it and decide what you think is appropriate. So maybe we think that linear might be appropriate there. We calculated the linear regression for this data, and you can see that equation they give us, y equals 0.7x plus 0.7. Then calculate the residuals. So if you look there on Desmos in that underneath your r squared and your r, you see where the word residuals, and it says E1, and then there's a little gray box that says plot. If you hit that plot button, Desmos will calculate your residuals for you. So in your table here in Desmos, it has now added in another column. And that column there is labeled E1. That is your residual plot. So to answer, calculate the residuals there for part D, we just did that. So we've got 0.6, negative 1.1, 0.7, negative 0.5, and 0.3. So remember, these are all distances that measure how far these y values that are in this table, so here are the y values in the table, this is a measure of how far their predicted y values would be from that, or the actual is from that predicted equation. So it's that distance, right? The distance between those lines there and, those points in that line. Right, if I want to see the actual residual plot, right, just maybe the plot, right down there next to the E1 that you see under the word residuals, you see in that little magnifying glass, right? If I click on it, all right, I'm also going to just put that back for a second. I can see just that residual plot, right, those red points. And if we look at it, all right, to answer that last question there, it says, do you believe that a linear model is appropriate for this data, and explain, right? We want to know, do those points look like they are randomly spaced above and below the x-axis, right? And if we do, right, then we are going to say that we think linear is appropriate. If we felt like they had that U-shaped pattern like we had seen, then we would think that a non-linear model would be appropriate for this set of data. And based on what I'm seeing there, I'm thinking that linear is appropriate because they do look like they are randomly spaced above and below that x-axis. If I didn't want to have that regression equation and I didn't want to have those original points in there, you can hide that stuff. All right, go over there and click on the little circle next to the regression equation, and if you click on the little circle next to y1, it'll eliminate those two things, so you can solely focus on just those residual points and deciding whether or not you feel that they are randomly spaced. So I think in this case they are. They don't look like they have that U-shaped pattern that we had seen in those previous examples of graphs. So do you believe that linear is appropriate? And I would say yes, right? The residuals are randomly spaced. above and below the x-axis. So if they are, then that means that linear is appropriate. All right, we've got another example here. We're going to do the exact same thing as we did there. So let's go over here and clear all this information out, and let's start over with our new table. And I'm going to hit my little magnifying glass so I can get an idea of what they look like. It then tells me to calculate the linear regression. And so here's our linear regression. Y equals negative 0.357x plus 16.333. I want to calculate those residuals. So again, on Desmos, under that word residuals, right, click that plot button. And it's going to create that new column in your table. And that new column in your table is going to have your residual values in it. So let's write those down. Negative 10.619, 0.095, 11.80, whoops, nope, that's actually going to be 11.810 because that 5 is going to round up that 9. 9.524, negative 1.762, and then negative 9.048. And so remember, those are the measures of the distance from where these y values, right, the y values that are in the table, right, these here. And then if I'd taken each of those x's and I had plugged it into that equation and gotten the y that produced, right, and subtracted, this is how we're getting those residual values. So let's hide that linear regression line. Let's also hide those points that were originally there so that we can focus solely on the residual plot. And if I'm looking at this residual plot, it appears to me that this does have a U-shaped pattern to it. And when we said it had a U-shaped pattern, then we said that that meant that a non-linear model is probably more appropriate than a linear model. So in this case, it asks, do we feel like linear is a linear relationship? I'm going to say no. The residual plot has a U-shaped pattern. Suggesting nonlinear is needed or appropriate. All right, there's one more example here. One more example, and I would ask that you possibly pause your video right here and you try this next one and then come back and restart and start the video again to see if you got this last one correct. So like I said, pause the video at this point, go and try number 3 on your own, and then come back and see how you did once you finish that. All right, so I went through and calculated the linear regression. Here it is. And then those residuals. And then again, I'm going to hide the regression equation. I'm going to hide those original points, and I'm going to look at just the residual plot itself. So these were just the residuals. And looking at it, I think that this was, yes, it does look linear because they are randomly spaced above and below the x-axis. So yes, linear is appropriate because the residuals are randomly spaced above and below the x-axis. Right, so hopefully you've had a second to check how you did. All right, you paused the video and you stopped and you did number 3. All right, the last little bit is going to kind of summarize all we've talked about here with regression, all right, between what we did on Friday and then what you've looked at today with these residuals. Right. So I think you might have a little bit of space somewhere. You can do that, but I want to just kind of summarize what we've kind of looked at. So if you're trying to decide what's the best type of model for a set of data, all right, first thing you can always do is use what we said is the eye test. Right, so actually looking at the scatter plot and kind of deciding what do you feel like it looks like. Does it look quadratic? Does it look linear? Does it look exponential? Right? If once you've looked at the eye test and you're still not quite sure, all right, maybe you can compare our squared values. Right? Remember, we want closest to 1. Is the best fit. We also talked about sometimes that maybe mathematically that r squared value says that 1 looks better than the other as far as an r squared value, it's closer to 1. But what is realistic? What logically makes sense? So that's your third thing to look at is what logically or what realistic, what is realistic for the context of the problem. So that's kind of something you need to check. So eye test, look at it, see what you feel like you might think it is. If you're still unsure, not quite sure, or maybe you even are sure, but you want to feel like you have some other data points to kind of back up your decision, compare the r squared values, look for the one that's closest to 1. You can always then think about realistically, you know, as we talked about the one with the rolling of the die, it didn't make sense for it to be quadratic because then that means you're putting die back into the problem, which it was not telling you to do. So think about it realistically. And then your fourth thing to kind of check, right, is that residual plot, which is what you looked at today. Right. Look at that residual plot. If it doesn't have any type of pattern to it, then you're going to know that a linear model is probably a good model for that set of data. If that residual plot has some type of U shape to it, then you're going to know that a nonlinear model would be the appropriate for that set of data. So that's kind of your checklist for when you're trying to decide what is the best type of function for that set of data. This is your kind of list to go through. All right, so at this point, the video is complete and you should start on your homework.